Why are we here? Where do we come from? These are the most enduring of questions, and it's an essential part of human nature to want to find the answers. Now we can trace our ancestry back hundreds of thousands of years to the dawn of humankind, but in reality our story extends far further back in time. Our story starts with the beginning of the universe. It began 13.7 billion years ago. And today it's filled with over 100 billion galaxies, each containing hundreds of billions of stars. In this series, I want to tell that story because ultimately we are part of the universe, so its story is our story. The force at the heart of this story is gravity. This fundamental force of nature built everything we see. It creates shape and order, and it initiates patterns that repeat across the heavens. But gravity also forges some of the most alien worlds in the cosmos. Worlds that defy belief. The quest to understand this fundamental force of nature has unleashed a golden age of creativity, exploration and discovery. And it's led to a far deeper understanding of our place in the universe. Every moment of our lives, we experience a force that we can't see or touch. Yet this force is able to keep us firmly rooted to the ground. It is, of course, gravity. But despite its intangible nature, we always know it's with us.
I'm going to ask you, how do you know that there's gravity around here? And you might say, well, it's obvious, I can just do an experiment, I can drop something. Well, yes, but actually, gravity is a little bit more subtle than that. But to really experience it, to understand it, you have to do something pretty extreme.
And this plane has been modified to help me do it. Thanks to its flight plan, it's known as the Vomit Comet. Once we've climbed to 15,000 meters, this plane does something no ordinary flight would do. Its engines are throttled back, and the jet falls to Earth. And then, something quite amazing happens. Simply falling at the same rate as the plane, for a few fleeting moments, we are all free of gravity's grip. this isn't just a joyride.
Now look, there's something very profound here, because although I'm falling towards the ground, you see, gravity has completely gone away. Gravity is not here anymore. I've cancelled gravity out just by falling. And if you understand that, then you will understand gravity.
So it is possible, by the simple act of falling, to get a very different experience of gravity. But this force of nature does more than just bring us back down to Earth. Gravity also plays a role on the grandest of stages, because across the universe, from the smallest mote of dust to the most massive star, gravity is the great sculptor that created order out of chaos. Since the beginning of time, gravity has been at work in our universe. From the primordial cloud of gas and cosmic dust, gravity forged the stars. It sculpted the planets and moons and set them in orbit around the newly formed suns. And gravity connects these star systems together in vast galaxies and steers them on their journey through unbounded space. Over the centuries, our quest to understand gravity has allowed us to explain some of the true wonders of the universe. But at a deeper level, that quest has also allowed us to ask questions about the origin and evolution of the universe itself. To understand how gravity works across the universe, we need look no further than the ground beneath our feet. Well, the first scientist to really think about it was Isaac Newton back in the 1680s. And he said this: gravity is a force of attraction between all objects. Now, the force of attraction between these two rocks is obviously very small, almost impossible to measure. And that's because the force is proportional to the masses of the objects. And these things are not very massive. But there is a more massive rock around here. So what I'm standing on, planet Earth. The mass of our Earth generates a gravitational pull strong enough to sculpt the entire surface of the planet. It causes water to gouge out vast canyons. It sets the limit for how high mountains can soar, and it shapes whole continents. But this invisible force does more than just shape our world. The skies are always changing. The constellations rise and fall in different places every night, and the planets wander across the background of the fixed stars. But throughout human history, there's been one constant up there in the night sky, because every human that's ever lived has gazed up at the moon and seen one face shining back at us. The reason why we never see the dark side of the moon is all down to the subtlety with which gravity operates. Millions of years ago, the moon rotated rapidly, but from the moment it was born, our companion felt the tug of gravity. Just as the moon creates great tides in our oceans, the Earth caused a vast tide to sweep across the surface of the moon. But This tide wasn't in water, it was in rock. Imagine that this is the moon, and over there is the Earth. The Earth's gravity acts on the moon and stretches it out into a kind of rugby ball shape. Now, the size of that tidal bulge facing the Earth is something like 7 meters in rock. And then as the moon rotates, that bulge sweeps across the lunar surface. I mean, imagine what that would look like here. You'd see a tidal wave sweep across this landscape with the rock rising and falling by 7 meters. This massive wave acted like a brake and gradually slowed the moon down. Eventually, the tidal bulge became aligned with the Earth, locking the speed of the moon's rotation. So the time it takes the moon to spin once is almost the same as the time it takes to orbit the Earth. So there is no dark side of the moon, just a side that gravity hides from our view. The bond that gravity creates between the Earth and the moon is repeated across the cosmos. It's the glue that holds the planets in orbit around the sun. And it binds our solar system and countless other solar systems together to form galaxies like our own Milky Way. But gravity's influence can be felt even further because it controls the fate of galaxies. When you look up into the night sky, then you see the universe as it looks in visible light, with the glowing of the stars and the galaxies. But that's only part of the story, because the universe is full of dust and gas, which you can't see with a conventional telescope, but you can see with a telescope like this. Radio telescopes, like the Very Large Array in New Mexico, are able to peer deep into space and reveal the incredible attractive power of gravity. This is Andromeda, a spiral galaxy roughly the same size and mass as the Milky Way. This island of over 1 trillion stars sits over 2.5 million light years away. But every hour, that gap shrinks by 500,000 kilometres. Whilst most galaxies have been rushing away from each other ever since they formed just after the Big Bang, some galaxies form so close together that they are locked in a gravitational embrace. Now, the Milky Way and Andromeda are 2 such galaxies, and computer simulations suggest that they will collide together in around 3 billion years' time. And look at that. That's a simulation of the Milky Way galaxy and the Andromeda galaxy colliding together. And all these wisps of smoke getting thrown out are stars. And these are star systems getting ripped out of the galaxy and thrown off into interstellar space. These 2 islands of hundreds of billions of suns have flown through each other, and gravity has exerted its grasp and dragged them back again. And just remember that we are one of those dots. You know, our sun and the Earth and the solar system are either going to be flung out into interstellar space, or they're going to be in here, in this maelstrom of hundreds of billions of suns swirling around each other and forming the core of a new galaxy. But just imagine what it would be like to gaze up at the sky as Andromeda approached, and the sky would be ablaze with the light of hundreds of billions of suns, and the imminent collision would provide the energy to generate the births of hundreds of millions more. What a magnificent sight it would be. But far more magnificent is the immense scale of gravity's embrace. It holds galaxies together across hundreds of billions of kilometres, and in doing so, it creates the most magnificent structures. Our own Milky Way is part of one of these, the Virgo cluster. Every point of light in this image is not a star, but a galaxy. There are 2,000 galaxies in this cluster, and they are all bound together by gravity, making it the largest structure in our intergalactic neighbourhood. There seems to be no limit to the reach or power of gravity. Its influence can be felt across the vast expanses of space and time. But there's something very interesting about gravity, because it is by far the weakest force of nature. I mean, look, I can pick this rock up off the ground, even though there's an entire planet Earth, trying to pull it down. So, if gravity is so weak, how come it's so influential? Gravity may be weak here on Earth, but it's not so weak across the cosmos. This invisible force varies on all the planets in the solar system and on the exoplanets we've discovered orbiting other suns. To experience what gravity feels like on these worlds, I need to go for a spin. This is a centrifuge. It was built in the 1950s to test whether fighter pilots had the right stuff, but it's going to allow me to feel what it'd be like to stand on the surface of any of the planets in the solar system that are more massive than the Earth, and in fact also what it'd be like to stand on some of the planets that we've found around distant stars.
Right, I'll just strap you in first of all. This is a go-to-go switch. It's an emergency switch in case something happens and you release it, the sensors will stop.
I was just told by the F-16 fighter pilot who's just been in here that it's 100 times more uncomfortable than being in a jet fighter. And I was kind of confident because I've been in jet fighters and didn't find it too uncomfortable, but apparently this is 100 times worse.
Doors closed again, protocols there, safe rooms are there, doctor is ready. We'll start up the centrifuge, Brian, and bring you in orbit, and it happens in 3, 2, 1 second from now.
The first planet I'm travelling to is Neptune. Its gravity is just fractionally stronger than here on Earth.
This is the gravitational field on Neptune, and you feel, you know what, I could probably get used to this. I could probably live on the surface of Neptune.
Can you lift your hands a little?
There we go.
Yeah, and down.
And it is actually quite an effort. It is noticeably heavier. It's like having a reasonably heavy weight in your hand.
You're ready to go to 2.5 G?
Yeah, so now we'll move from Neptune to Jupiter.
Let's go there.
Jupiter is over 1,300 times more massive than the Earth, but because it's mostly gas, it's not very dense, so its gravity is just over twice as strong at its surface.
Well, now actually it is quite difficult to lift my hand, and that's 2.5 G. I wouldn't want to sit here for half an hour.
And can you lift both of your hands above your head and see what happens
Let's
there?
see. So actually, just about, but actually it's an immense amount of hard work. So it would be hard work living on Jupiter.
Let's go to 4G.
Actually, this is heading to a planet around a planet called Ogle 2 TR L9b, which is around a star in the constellation of Carina. It's one of the exoplanets we've discovered. Oh, and there we go. Now that is actually beginning to feel quite unpleasant.
Can you describe what you're feeling?
A very heavy face.
Alright.
My head is extremely heavy.
How about your lungs? Inhaling, exhaling, breathing?
It's much harder work. I can't lift my hand off my leg.
Okay.
And that's at 4G.
Yeah.
But my head and my face feel very, very heavy.
Yeah.
It's quite an unpleasant feeling.
We'll go to 5 and let me know if you have any visual disturbances.
I'm now en route to a newly discovered exoplanet, WASP 8b.
4.4.
This world sits in the small and faint constellation of Sculptor.
Quite hard to speak.
It has a gravitational force nearly 5 times that of the Earth.
Alright, we'll go to 5G.
Oh, very foggy.
Okay.
Very foggy.
Very foggy. Still foggy?
Yeah.
Alright.
Take it down.
Okay, we'll take you down.
Very interesting.
It was, wasn't it?
My face felt a bit saggy there.
Well, you looked a little different.
Quite unpleasant that time actually. So it went very quickly up to 5G. And what happens is, well for me anyway, is vision becomes very, very foggy. Just the whole thing just blurs and blurs and blurs. So you realise that we're obviously very finely tuned to live on a planet that has an accelerator-induced gravity of 1G. When you go to 2G, it's difficult. When you go to 3G and 4G, it becomes unpleasant. And 5G, anyway, for me, was on the border of being so unpleasant that you pass out.
So although gravity feels weak here on Earth, it certainly isn't weak everywhere across the universe. And that's because gravity is an additive force. It scales with mass, so the more massive the planet or star, the stronger its gravity. The body with the strongest gravity in our solar system is the Sun. Our star has so much mass packed inside a relatively small space that it has a gravitational pull at its surface 28 times that of the Earth. If I were able to set foot on this world, all the blood would be pulled out of my upper body, and I would die in less than a minute. But our sun's gravitational force is nothing compared to the extreme G found at the surface of one of the strangest places in the universe. Imagine the gravity on a world with more mass than our sun, crammed into a sphere just 20 kilometres across. We first detected such a wonder just 40 years ago, but the story of its discovery begins over 1,000 years earlier. This is Chaco Canyon in New Mexico in the southwestern United States, and it was home to what's become known as the Chacoan civilization. Well, this is Pueblo Bonito, one of the so-called Chacoan great houses. And back in the 1100s, this place had over 600 rooms. It's thought that this building must have been ceremonial or religious, a cathedral, if you like. The Chacoan great houses are aligned with interesting objects in the sky, so the point at which the sun and moon rise at important times of the year. So it seems that by constructing these grand buildings, the Chacoans were not only trying to place themselves at the heart of local culture, but also to place themselves at the heart of the cosmos. Very little is known about the Chacoan culture because no written text has ever been discovered. But in another part of the canyon, there is a record of a spectacular event that they witnessed in the sky in 1054. I've known about this place since I was about 12 or 13 years old, and the reason is this book and the television series Cosmos, Carl Sagan's masterpiece. Probably the most important reason that I got interested in astronomy. On page 232, there's a picture that's always fascinated me and captured my imagination, and it's a photograph of that wall of rock, and in particular a painting that's on the overhang, because it's thought that that painting is a record of one of the most spectacular and magical events in the cosmos. On July 4th, 1054 AD, a bright new star appeared, and it outshone every other star in the night sky for over 3 weeks. It was so bright that it was visible in the daytime. And it's thought that this painting is the Chacoan people's record of that astronomical event. And the reason we think that is that using modern computer techniques, you can wind back the night sky and say, where would the moon have been? Where would the stars have been? And you find that in that direction, the moon would have risen and tracked across the night sky, and the new star would have been very, very close to the crescent moon. We now know that that new star was in fact the explosive death of an old star, a supernova explosion. a star literally blowing itself apart at the end of its life. Throughout a star's life, there is a constant battle between energy pushing out and gravity pushing in. As long as the star burns, the two forces balance each other out. But when it runs out of fuel, gravity wins, and the star collapses and then explodes with the brightness of 1 billion suns. We can no longer see the supernova that Vikshåland saw, but we can still marvel at what it left behind. This is the Crab Nebula, the remains of that exploding star that the Vikshåland saw in these skies 1,000 years ago. It's an expanding cloud of gas and dust, the remains of that dying star. The colours are different chemical elements, so the orange is hydrogen, the red is nitrogen, and those filaments of green are oxygen. While the explosion blew most of the stellar material out into the cosmos to form this vast nebula, we now know that this wasn't the end of the story. At the centre of the nebula lies the remnant of the star, its core crushed by the force of gravity. That is a neutron star, an image taken by the Chandra X-ray satellite. Central blob there is only about 20 kilometres across, but it's got the mass of our sun, a star the size of a city. It's spinning at a rate of over 30 times a second, 1,800 revolutions per minute. And it really is an astonishingly alien world. As the neutron star spins, jets of particles stream out from the poles at almost the speed of light. These jets are powerful beams that sweep around as the star rotates. When the beams sweep across the Earth, they can be heard as regular pulses, so we call them pulsars. But it's not this rhythmic noise that makes the crab pulsar a wonder. It's the extraordinary nature of gravity on this alien world. If I were to be on its surface, then the gravitational pull on me would be 100,000 million times that I feel on Earth. That means that if I were to jump from the top of that projection screen, and by the time I hit the ground, I'd be travelling at over 4 million miles an hour. That's a lot of gravity. Pulsars have such extreme gravity because they're made of incredibly dense matter. To understand why, we have to look at what gravity can do to matter at the very smallest scales. Everything in the universe is made of atoms, and until the turn of the 20th century it was thought that they were the smallest building blocks of matter. I mean, the word itself comes from the Greek atomos, which means indivisible. But we now know that atoms are made of much smaller stuff. Atoms consist of an atomic nucleus surrounded by a cloud of electrons. And whilst almost all of the mass is contained in the nucleus, it is incredibly tiny compared to the size of an atom. And if this were a nucleus, then the cloud of electrons would stretch out to something like a kilometre away. I mean, that's from here to that rock. And electrons on this scale are incredibly tiny. They're just like specks of dust, and there aren't many of them. So imagine a giant sphere centred on the atomic nucleus, stretching out all the way to that rock and beyond, with just a few points of dust in it. That's an atom. So that means that matter is almost entirely empty space. I'm full of empty space. The Earth is full of empty space. Everything you can see in the universe is pretty much just empty space. So if everything in the universe is made up of atoms, and atoms are 99.9999% empty space, then most of the universe is empty. But in the Crab pulsar, the force of gravity is so extreme that the empty space inside the atoms is squashed out of existence. So all you're left with is incredibly dense matter. Imagine this was matter taken from a neutron star, then it would weigh more than Mount Everest. Or, to put it another way, if I took every human being on the planet and squashed them so they were as dense as neutron star matter, then we would all fit inside that. And if I were to drop my neutron star stuff to the ground, then it would slice straight through the earth like a knife through butter. Wherever we look in the universe, we see gravity at work. It creates shape and structure. It governs the orbits of every planet, star and galaxy in ways we thought we were able to predict. But there was a flaw in our understanding of this force, and it was exposed by one of our close neighbours. This is Mercury. For thousands of years we've marvelled as this fleet-footed planet races across the face of the sun. But 150 years ago, astronomers noticed something strange about Mercury's orbit. Imagine that this rock is the sun, and this is Mercury. Now Mercury has quite a complex orbit. For one thing, it's not a perfect circle, it's quite an elongated ellipse. So its closest approach to the sun, it's around 46 million kilometres away, and then it drifts out to something just under 70 million kilometres. But you can calculate Mercury's orbit very precisely using only Newton's laws of gravity. So astronomers used to predict the exact time when you could look up into the sky, look at the sun, and see the tiny disk of Mercury pass across its face. The thing was, they never got it right. They predicted it time and time again, and every time it happened, they got it slightly wrong, which was an immense embarrassment. So what they did was that rather than question Newton, they invented another planet, and they called it Vulcan. And they said that there must be another planet somewhere in the solar system which is always invisible from Earth, but which perturbed Mercury's orbit a bit. And so that was the reason their calculations were wrong. For decades, astronomers searched and searched for Vulcan. But they never found it, because Vulcan didn't exist. The explanation, the real explanation, was even more interesting than inventing the planet Vulcan, because it required a modification In fact, a complete rewriting of Newton's law of gravity. Gravity is not a force pulling us towards the centre of the Earth like a giant magnet. In a sense, gravity isn't really a force at all. Describing the nature of gravity turned out to be one of the great intellectual challenges. But almost 200 years after Newton's death, a new theory emerged. The new theory, called general relativity, was published in 1915 by Albert Einstein after 10 years of work, and it stands to this day as one of the great achievements in the history of physics. See, not only was it able to explain with absolute precision the strange behaviour of Mercury, but it explains to this day everything we can see out there in the universe that has anything to do with gravity. And, most importantly of all, it explains how gravity actually works. Gravity is the effect that the stars, planets and galaxies have on the very space that surrounds them. According to Einstein, space is not just an empty stage, it's a fabric called space-time. This fabric can be warped, bent and curved by the enormous mass of the planets, stars and galaxies. You see, all matter in the universe bends. The very fabric of the universe itself. Matter bends space. I bend space. These mountains bend space, but by the tiniest of amounts. But when you get onto the scale of planets and stars and galaxies, then they bend and curve the fabric of the universe by a very large amount indeed. And here is the key idea. Everything moves in straight lines over the curved landscape of space. Everything moves in straight lines over the curved landscape of space-time. So what we see as a planet's orbit is simply the planet falling into the curved space-time created by the huge mass of a star. This is able to explain Mercury's erratic orbit. Because of the planet's proximity to our Sun, the effects of the curvature of space-time matter far more for Mercury than for any other planet in the solar system. Now, this idea of curved space is difficult to imagine, but we can only step outside of it. We can only float above space-time and look down on it. This is what our universe would look like. You would see the mountains and valleys. You would see the little peaks and troughs created by planets and moons. And you would see these vast, deep valleys created by the galaxies. And you would see planets and moons and stars circling the peaks as they follow their straight line paths through the curved landscape of space-time. So one way to think about gravity is that everything in the universe is just falling through space-time. The moon is falling into the valley created by the mass of the Earth. The Earth is falling into the valley created by the Sun, and the solar system is falling into the valley in space-time created by our galaxy. And our galaxy is falling towards other galaxies in the universe. Einstein's theory of general relativity is so profound, so beautiful, that it can describe the structure and shape of the universe itself. But remarkably, the theory can also predict its own demise, because it predicts the existence of objects so dense, so powerful, that they warp and stretch and bend the structure of space-time so much that they can stop time, and that they can swallow light. These are objects so powerful that they can tear all the other wonders of the universe apart. Since the dawn of civilization, we've peered at the stars in the night sky and tracked the movements of the planets. We see these familiar patterns repeated across the whole universe. But when we train our telescopes to the stars that orbit around the centre of our galaxy, we see something very unusual. Well, this is one of the most fascinating and important movies made in astronomy over the last 10 or 20 years. This is real data. Every point of light in this movie is a star orbiting around the centre of our galaxy. They're known as the S-stars. Now, our Sun takes around 200 million years to make its way around the Milky Way. One of these S-stars takes only 15 years to go around the centre of the galaxy. It's travelling at 3,000 or 4,000 kilometres per second. Now, by tracking the orbits, it's possible to work out the mass of the thing at the centre. The answer took astronomers by surprise, I think it's fair to say, because the object in the centre of our galaxy is 4 million times as massive as the Sun, and it fits into a space smaller than our solar system. Now, there's only one thing that anyone knows of that can be so small and yet so massive, and that's a black hole. So what we're looking at here is stars swarming like bees around a supermassive black hole at the centre of the Milky Way galaxy. We think black holes can be smaller than an atom or 1 billion times more massive than our Sun. Some are born when a star dies. When a star around 15 times the mass of our Sun collapses. All the matter in its core is crushed into an infinite void of blackness known as a stellar mass black hole. Black holes are the most extreme example of warped space-time. They have such enormous mass, crammed into such a tiny space that they curve space-time more than any other object in the universe. The immense gravitational pull of these monsters can rip a star apart. They tear matter from its surface and drag it into orbit. This superheated matter spins around the mouth of the black hole, and great jets of radiation fire from the core. Although these jets can be seen across the cosmos, the core itself remains a mystery. Black holes curve space-time so much that nothing, not even light, can escape. So their interior is forever hidden from us. But because we understand how matter curves the fabric of space, it is possible to picture what is happening. Near a black hole, space and time do some very strange things, because black holes are probably the most violent places we know of in the universe. This river provides a beautiful analogy for what happens to space and time as you get closer and closer to the black hole. Now upstream the water is flowing pretty slowly. Let's imagine that it's flowing at 3 kilometers per hour and I can swim at 4. So I can swim faster than the flow and can easily escape. But as you go further and further downstream towards the waterfall in the distance, the river flows faster and faster. Imagine I was decide to jump into the river just there on the edge of the falls. The water is flowing far faster than I could swim. So no matter what I did, no matter how hard I tried, I would not be able to swim back upstream. I would be carried inexorably towards the edge and I would vanish over the falls. Close to a black hole, because space flows faster and faster and faster towards the black hole. Literally, this stuff, my space that I'm in, flowing over the edge into the black hole. And at the very special point called the event horizon, space is flowing at the speed of light into the black hole. Light itself, travelling at 300,000 kilometers per second, is not going fast enough to escape the flow, and light itself will plunge into the black hole. Well, as you fall into a black hole across the event horizon, then if you were going feet first, your feet will be accelerating faster than your head. So you would be stretched, and you would be quite literally spaghettified. you get right to the centre, then our understanding of the laws of physics breaks down. Our best theory of space and time, Einstein's theory of general relativity, says that space and time become infinitely curved, that the centre of the whole becomes infinitely dense. That place is called a singularity, and it is the place where our understanding of the universe stops. Gravity is the great creator, the constructor of worlds. That's because it's the only force in the universe that can reach out across the vast expanses of space and pull matter together to make the planets, the moons, the stars, and the galaxies. But gravity is also the destroyer, because it's relentless, and for the most massive objects in the universe, for the most enormous stars and the centres of galaxies, gravity will eventually crush matter out of existence. Now, the word beautiful is probably overused in physics. I probably overuse it. But I don't think there is any scientist who would disagree with its use in the context of Einstein's theory of gravity. Because here is a theory that describes a universe that is bent and curved out of shape by every moon, every star, and every galaxy in the sky. But I don't think there is any scientist who would disagree with its use in the context of Einstein's theory of gravity. Because here is a theory that describes a universe that is bent and curved out of shape by every moon, every star, and every galaxy in the sky. And everything in the universe has to follow those curves, from the most massive black hole to the smallest mote of dust, even to beams of light. But the most tantalising thing about Einstein's theory of gravity is we know that it's not complete. We know that it's not the ultimate description of the structure and shape of the universe. And that, for a scientist, is the most beautiful place to be, on the border between the known and the unknown. That is the true wonder of the universe. There's so much more left of it to explore.
Van Gogh's The Theory here on BBC HD tomorrow at 8. And coming up next tonight, exploring a betrayal of trust on an epic scale with the story of former priest Brendan Smith. Next.
Why are we here? Where do we come from? These are the most enduring of questions, and it's an essential part of human nature to want to find the answers. We can trace our ancestry back hundreds of thousands of years to the dawn of humankind, but in reality, our story extends far further back in time. Our story starts with the beginning of the universe. It began 13.7 billion years ago. And today, it's filled with over 100 billion galaxies, each containing hundreds of billions of stars. In this series, I want to tell that story because ultimately we are part of the universe, so its story is our story. This film is about the stuff that makes us and where it all came from. Because understanding our own origins means understanding the lives of stars and how their catastrophic deaths bring new life to the universe. Because every mountain, every rock on this planet, every living thing, every piece of you and me was forged in the furnaces of space. In the Nepalese capital city of Kathmandu, and Hindus come here from all over India and Nepal to worship the god Shiva. In fact, that is Shiva's temple. Now, Shiva is the god of destruction. In the Hindu faith, everything has to be destroyed so that new things can be created. And that's why pilgrims come here to the banks of the Bagmati river at the foot of Shiva's temple. The belief in this cycle of creation and destruction lends Pashupatinath an added significance. Many of these pilgrims will have come here at the end of their lives, to die here and be cremated. Hindus believe in reincarnation, an eternal sequence of death and rebirth. Cremation helps free the soul so it's ready for the next life. They also believe that the physical elements of the body are released back to the world so they can be recycled in the next stage of creation. It's an ancient belief that touches on a deeper truth about how the universe works. Every civilization, every religion across the world has a creation story. It tells of where we came from, of how we came to be here, and of what will happen when we die. Well, I have a different creation story to tell, and it's based entirely on physics and cosmology. Now, it can tell us what we're made of and where we came from. In fact, it can tell us what everything in the world is made of and where it came from. It also answers that most basic of human needs to feel part of something much bigger. Because to tell this story, you have to understand the history of the universe. And it teaches us that the path to enlightenment is not an understanding of our own lives and deaths, but the lives and deaths of the stars. My creation story is the story of how we were made by the universe. It explains how every atom in our bodies was formed not on Earth, but was created in the depths of space through the epic life cycle of the stars. And to understand that story, we will journey to the stars in all their stages of life. This is where stars are born, a nebula, a stellar nursery where new stars burst into life. Those stars will burn for billions of years until their voracious hunger for fuel forces them to blow up to become giants. Hundreds of times the size of our sun. And when they die, stars go out with the biggest bang in the universe. But to understand how we came from the stars, we must begin our journey much closer to home. Sunrise over Nepal, and those are the tallest mountains in the world, the Himalayas. I mean, every one of those peaks is over 6,500 metres. What a spectacular sight. But it's incredible to think that just a few tens of millions of years ago, those mountains were something very different. The Himalayas haven't always been mountains. We can find clues to their true origin by looking at them more closely. This is Himalayan limestone, the rock out of which much of this magnificent mountain range is made. Now, if you look closely, you can see a kind of chalky, granular structure, because limestone is made primarily out of the bodies, the shells of dead sea creatures, of coral and polyps. And when they die, they're put under immense pressures and squashed and eventually form limestone. So the Himalayas were once living creatures. Much of the rock in the Himalayas was formed at the bottom of an ocean, and then over millions of years it was raised up to become these vast peaks. We've even found fossils at the top of Mount Everest. It's a beautiful example of the endless recycling of the Earth's resources that has been going on since the dawn of time. And we are part of that system. Every atom in my body was once part of something else. So an ancient tree, or a dinosaur, or a rock. In fact, definitely a rock. And the reason that the rocks of the earth can become living things, and then living things will return to the rocks of the earth, is because everything is made of the same basic ingredients. Those ingredients are the chemical elements, the building blocks of everything on earth. Elements like hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium. Everything in the world is made up of the same basic set of chemical elements, just assembled in different ways. So these mountains, the Himalayas, are made of limestone, and that's calcium carbonate. Now, calcium, carbon and oxygen are three of the elements that are vital for life. So calcium in my teeth and bones, oxygen in the air that I breathe, and carbon in every organic molecule in my body. Now, you're probably pretty familiar with those elements in their combined forms, but you very rarely see the elements on their own. There's a good reason why many of the elements are not found in their raw forms in nature. They're extremely reactive. This is sodium. As you can see, it's a silvery metal, and it's also quite reactive. In fact, it's so reactive that when you drop it into water, you get a violent, almost explosive reaction, which is all the more surprising when you think that when combined with chlorine, this forms sodium chloride, salt.
which is vital for life. Excellent. And that's why I love chemistry almost as much as physics.
It's this reactivity that enables the elements to combine with one another to make new substances.
Where the hell's it going?
That, in turn, has allowed the Earth to develop its endless variety. And that variety includes us. So to explain where we come from, we must also explain where the elements come from.
We now know that the Earth is made of 92 chemical elements. And that's pretty amazing if you think of the complexity that we see around us. We also know that everything beyond Earth, everything we can see in the universe, is made of those same 92 elements. And notice that I didn't say we think that that's what they're made of. I said we know that's what they're made of, because we can prove it.
The chemistry set we have on Earth extends far beyond the planet. We've set foot on the moon and know that it's rich in helium, silver, and water. We've sent robot landers to our neighbouring planets and discovered that Mars is rich in iron, which has combined with oxygen to form its familiar rusty red colour. And we know that Venus's thick atmosphere is full of sulphur. We've sent spacecraft to the edge of the solar system to discover that Neptune is rich in organic molecules like methane. But what of the rest of the universe? It seems impossible that we could discover what the stars are made of, because they're so far away. Even the nearest star, Proxima Centauri, is 10,000 times more distant than Neptune, 4.2 light years from Earth. And the nearest galaxy, Andromeda, is another 2.5 million light years away. Yet despite these vast distances, these alien worlds are constantly sending us signals, telling us exactly what they're made of. Our only contact with the distant stars is their light that's journeyed across the universe to reach us, and encoded in that light. Our only contact with the distant stars is their light that's journeyed across the universe to reach us, and encoded in that light is the key to understanding what the universe is made of. And it's all down to a particular property of the chemical elements. You see, when you heat the elements, when you burn them, then they give off light. And each element gives off its own unique set of colours. So this is strontium, and it burns with a beautiful red colour. Sodium is yellow. Potassium is lilac, and copper is blue. Each element has its own characteristic colour. It's this property that tells us what the stars are made of. But it's a little more complicated than simply looking at the colour of the light that each star emits. You can see why by looking at the light from our nearest star, the Sun. This is a spectrum of the light taken from our Sun. And at first glance it looks very familiar. It looks like a stretched out rainbow, because that's exactly what a rainbow is. It's the spectrum of the light from the Sun in the sky. But if you look a bit more closely, then you see that this spectrum is covered in black lines. These are called absorption lines. Each element within our sun not only emits light of a certain colour, it also absorbs light of the same colour. By looking for these black lines in the sun's light, we can simply read off a list of its constituent elements, like a barcode. For example, these two black lines in the yellow bit of the spectrum, sodium, you can see iron. Right down here, you can see hydrogen. So by looking at these lines in precise detail, you can work out exactly what elements are present in the sun. And it turns out that that's about 70% hydrogen, 28% helium, and 2% the rest. And you can do this not only for the sun, but for any of the stars you can see in the sky, and you can measure exactly what they're made of. So that star there is Polaris, the pole star, and you can see that because all the other stars in the night sky appear to rotate around it. Now it's 430 light years away. But we know just by looking at the light that it has about the same heavy element abundance as our sun. But it's got markedly less carbon and a lot more nitrogen. And the same applies for other stars. Vega, the second brightest star in the northern sky, has only about a third of the metal content of our sun. Whereas other stars are metal heavy. Sirius, the dog star, contains 3 times as much iron as the sun. And Proxima Centauri is rich in magnesium. But although the quantities of the elements may vary, wherever we look across space, we only ever find the same 92 elements that we find on Earth. We are made of the same stuff as the stars and the galaxies. But where did all this matter come from? And how did it become the complex universe we see today?
In order to understand where we came from, we have to understand events that happened in the first few seconds of the life of the universe. See, when the universe began, it was unimaginably hot and dense. I mean, we literally don't have the scientific language to describe it. But it was, in a very real sense, beautiful. That there was no structure, certainly no matter. It was exactly the same, whichever way you look at it.
We can get some idea of how the universe developed from this state of pure symmetry by looking at the behaviour of water in this remarkable landscape. These are the Altatio geysers, high in the Chilean Andes. As the boiling water bubbles up through the ground to meet the freezing mountain air, water can be found in all 3 of its natural phases: vapour, liquid and ice. In its hottest state, water is, like the early universe, an undifferentiated cloud. But as it cools, it suddenly behaves very differently.
You see, if you look at a cloud of steam, it looks the same from every direction. But as it cools down, as it lands on this plate of freezing cold glass, then
it immediately crystallises out, it turns into solid water, ice.
As the ice crystals form, the symmetry of the water vapour disappears from view, and complex, beautiful structure emerges.
In the same way, we think that the universe, as it cooled, went through a series of these events where structure emerged. One of the most important was about 1 billionth of a second after the Big Bang.
In that moment, an important part of the symmetry of the universe was broken. Known as electroweak symmetry breaking, this was the moment when subatomic particles acquired mass, substance, for the first time. Amongst them were the quarks. As the universe continued to cool, those quarks joined together to form larger, more complex structures called protons and neutrons.
Way before the universe was a minute old, the quarks had been locked away inside the protons and the neutrons, and they are the building blocks of all atomic nuclei, the building blocks of the elements.
These same protons and neutrons are with us to this day. They form the hearts, the nuclei, of all atoms. Just a few seconds after the beginning of the universe, the fundamental building blocks of everything had been created.
Well, it sounds ridiculous, you know, the fact that everything you need to make up me and everything on planet Earth, and in fact every star and every galaxy in the sky was there after the first minutes in the life of the universe. It's almost unbelievable, but we have extremely strong experimental evidence to suggest that that is the way that it is. But from that point on, it was just, in a sense, a process of assembling those bits into more and more complex things. That is an incredibly fascinating story in itself.
To tell that story, we must look deep inside the atom, to the nucleus at its centre. Here, we can see how protons and neutrons are assembled to build up the 92 different elements.
Now, the wonderful thing about the construction of the chemical elements is that it's so simple. I suppose you could call it child's play. So imagine these bubbles are my universal chemistry set. And then single bubbles would just be single protons. That's the nucleus of the simplest chemical element.
The element with a single proton in its nucleus is hydrogen. And from hydrogen, you can make all the other elements. The first stage is to stick two protons together.
Look at that! That was two bubbles stuck together. And what happens when you stick two protons together is one of the protons turns into a neutron. Now that is called deuterium.
Deuterium is still a form of hydrogen because it has only one proton in its nucleus, and it's the number of protons that defines the element. It's only when two deuterium nuclei are combined that a new element is created.
Take two deuteriums and fuse them together, and you get a nucleus with two protons and two neutrons. That's helium, the second simplest element.
And then it's just a question of adding more and more protons and neutrons.
Well, there's an incredibly complicated nucleus. That's about 12 things stuck together. So that would be probably carbon 12, which is 6 protons and 6 neutrons. And you can carry on building more and more complex elements all the way up to the heaviest element in the universe, to uranium and beyond. Simple and beautiful physics.
This process of building the elements is called nuclear fusion. It allows the simplest of ingredients to create the infinite variety of the universe. But although this bubble metaphor makes creating new elements seem simple, it is in reality incredibly difficult to achieve. So difficult that there's only one place in nature that it happens. It's in stars like our sun that the elements are assembled. They are the only places in the universe hot enough and dense enough to fuse atoms together. Even then, only a fraction of the star reaches the extreme temperatures necessary. The sun is 6,000 degrees Celsius at its surface, not nearly hot enough to power fusion. But deep below, where the temperature reaches 15 million degrees, the sun fuses hydrogen into helium at a furious rate. Every second, it burns 600 million tons of hydrogen. As it does so, it releases the huge amounts of heat and light that brings our planet to life. It is this process of converting that allows us to exist.
For all its power, the sun only converts hydrogen, the simplest element, into helium, the next simplest. But there are over 90 other elements present in our universe. So where did they all come from?
If the heavier elements are not being made in stars like the sun, then there must be somewhere else in the universe where they are assembled. It's important to know because it's the elements beyond helium that give our world its complexity. And when it comes to planet Earth and human beings, there's one element that is particularly important: carbon.
Life is completely dependent on carbon. I mean, I'm made of about 1 billion carbon atoms, as is every human being out there, every living thing on the planet. Imagine how many carbon atoms that is. So where does all that carbon come from? Well, it comes from the only place in the universe where elements are made: stars. But in order for us to live, a star must die.
Stars in the prime of their lives, like our sun, are only hot enough to make helium. Forming the heavier elements requires much higher temperatures. Temperatures that can only be reached at the end of a star's life. Looking out into space, you might think that the cosmos is a constant, unchanging place, that the stars will always be there. But in fact, the stars are only a temporary feature in the sky, and though they may burn brightly for many millions or billions of years, they can only live for as long as they have a supply of hydrogen to burn. When a star runs out of hydrogen, it begins to die, but it doesn't go quietly. Rather than cooling, the star becomes much hotter until there's a sudden flash. Then the star starts to expand. Over tens of thousands of years, it balloons to many hundreds of times its previous size. But in this bloated state, the star is unable to maintain its surface temperature. As it cools, it takes on the characteristic colour of a dying star. It has become a red giant.
These are pictures of a red giant star in our galaxy, a star called Betelgeuse. Now it's one of our nearest neighbours in cosmic terms. It's only about 600 light years away. But it's the size that's astonishing. Maybe to put the sun there, then Venus would be back there, and the Earth back there, and Mars here. And in fact, you could fit everything in the solar system all the way out to Jupiter inside the star. Now, because it's so big, even though it is 600 light years away, you can see detail on its surface. So these are sunspots on the surface of Betelgeuse. But it's not what's going on the surface that's really interesting. To understand where carbon comes from in the universe, we have to understand what's going on deep in the heart of the star. Imagine this old prison in Rio is a dying star like Betelgeuse. There is the bright surface shining off into space. As I descend deeper and deeper into the prison, the conditions will become hotter and hotter and denser until down there in the heart of the star is the core, and it's in there that all the ingredients of life are made.
Deep in its core, the star is fighting a futile battle against its own gravity. As it desperately tries to stop itself collapsing under its own weight, new elements are made in a sequence of separate stages. Stage 1 is while there is still a supply of hydrogen to burn.
Whilst the star's burning hydrogen to helium in the core, vast amounts of energy are released, and that energy escapes, literally creating an outward pressure which balances the force of gravity and, well, it holds the star up and keeps it stable. But eventually, the hydrogen in the core will run out, and at that point, the fusion reactions will stop, no more energy will be released, and that outward pressure will disappear. Now, at that point, the core will start to collapse very rapidly, leaving a shell of hydrogen and helium behind.
Beneath this shell, as the core collapses, the temperature rises again, until at 100 million degrees, stage 2 starts, and helium nuclei begin to fuse together.
A helium fusion does two things. Firstly, more energy is released, and so the collapse is halted. But secondly, two more elements are produced in that process. Carbon, oxygen, two elements vital for life. So this is where all the carbon in the universe comes from.
every atom of carbon in my hand, every atom of carbon in every living thing on the planet was produced in the heart of a dying star. But compared to the lifetime of the star, the creation process of carbon and oxygen is over in a blink of an eye, because in only about 1 million years the supply of helium in the core is used up. And for stars as massive as the Sun, that's where fusion stops, because there isn't enough gravitational energy to compress the core any further and restart fusion. But for massive stars like Betelgeuse, the fusion process can continue. When the helium runs out, gravity takes over again, and the collapse continues. The temperature rises once more, launching stage 3, in which carbon fuses into magnesium, neon, sodium and aluminium. And so it goes on. Core collapse, followed by the next stage of fusion to create more elements. Each stage hotter and shorter than the last. And eventually, in a final stage that lasts only a couple of days, the heart of the star is transformed into almost pure iron, whose chemical symbol is Fe. This is where the fusion process stops. In its millions of years of life, the star has made all the common elements, the stuff that makes up 99% of the Earth. The core is now a solid ball of those elements, stacked on top of each other in layers. On the outside, there's a shell of hydrogen. Beneath it, a layer of helium. Then carbon and oxygen and all the other elements, all the way down to the very heart of the star. And once that has fused into solid iron, the star has only seconds left to live. When a star runs out of fuel, then it can no longer release energy through fusion reactions. And then there's only one thing that can happen. In about the same amount of time it takes this prism block to crumble, the entire star falls in on itself. This is the destiny that awaits most of the stars in the universe. Yet even the implosion of a star only forges the first 26 elements. What of the remaining elements, some of which are vital for life, and many of which we hold most precious? These are the remote forests of Northern California. 100 years ago, this whole area was teeming with people, all in search of one element. And the reason they were here can still be found in the original 16:1 mine. This one stood at the centre of the California gold rush, and thanks to a quirk of geology, it continues to yield its precious bounty over 100 years later. Now, the unique thing about this place is that it sits right on the divide between the North American plate and the Pacific plate. You see a divide there between the rock and quartz, and right up there you can see the top of it. Now, in between the faults,
this rock, the quartz, formed then 140 million years ago in the Jurassic period, when the dinosaurs were running around above our heads. Hot water welled up and flowed. That water deposited the gold through the seams of quartz. And so all the miners have to do, all they have to do is follow the seams of quartz, and over hundreds of years they found vast amounts of gold deposited there. Well, this is what all the fuss is about. This is the gold as it comes out of the ground, and it's unusually pure as gold goes. This is about 85% pure gold, but it can also be found like this. And this is a gold nugget that was found in a river, on a riverbed, and it's a heavy piece of gold. It's between about 1 and 1.5 ounces, which means that at today's prices it's worth about $2,000. And it's that inherent value that makes mines like this worth operating.
But there's something a bit odd about the value we attach to gold. Throughout history, people have gone to extraordinary lengths to get their hands on this most precious substance, which is strange, because it isn't particularly useful for anything.
Most of the gold that's been extracted throughout human history has ended up as jewellery. But it has got one thing going for it, and that's that it is incredibly rare.
When we look out into space, we are looking into our own origins. Because we are truly children of the stars. And written into every atom and every molecule of our bodies is the entire history of the universe, from the Big Bang to the present day.
Our story is the story of the universe. Every piece of everyone, of everything you love and everything you hate, of the thing you hold most precious, was assembled by the forces of nature in the first few minutes of the life of the universe, transformed in the hearts of stars, or created in their fiery deaths. And when you die, those pieces will be returned to the universe in the endless cycle of death and rebirth. What a wonderful thing it is to be a part of that universe. And what a story. What a majestic story.
When we look out into space, we are looking into our own origins. Because we are truly children of the stars. And written into every atom and every molecule of our bodies is the entire history of the universe, from the Big Bang to the present day.
Our story is the story of the universe. Every piece of everyone, of everything you love and everything you hate, of the thing
you hold most precious was assembled by the forces of nature in the first few minutes of the life of the universe, transformed in the hearts of stars, or created in their fiery deaths. And when you die, those pieces will be returned to the universe in the endless cycle of death and rebirth. What a wonderful thing it is to be a part of that universe. And what a story. What a majestic story.